All right, we're going to be looking at growth and decay functions, and it looks something like this, where you've got y equals a times b to the x, where a is your initial value. Now your initial value in this case would be 3. Your initial value is always going to be what you get when x equals 0. Okay, so that's always going to be your initial value. So in this case, if we were making a function for this table, it would be y equals 3. 3 is my initial value, what I got for y when x equals 0. And then you have your growth or decay factor, your b term here. And the way that I'm going to get that is by dividing. And I can pick any number on this table, say I pick 12, and divide it by the one above. So if I were to say 12, in this case 12 divided by 6, that's going to give me 2. So the this is growth. If the number that you get is bigger than 1, it's going to be growth. 2 is bigger than 1, so I know this is a growth function. When I plug in numbers for x, I'm going to get outputs that are bigger and bigger. So what's happening here is they are multiplying by 2 every time. So they started with 3, and then it was 3 times 2 to the x power, and whatever number you plug in, it's going to end up giving you that specific output. Now, whether or not the function is growth or decay doesn't really matter. I'm always going to do the same thing. I'm always going to find the initial amount by looking at where x equals 0. Whatever the output is, that's my initial amount. So when x equals 0, y equals 4. That's my a term, my initial amount. Then I'm going to find the b term by dividing any number in this table by the number above. So let's say I took 1 and I divided it by 2. Well, 1 divided by 2 gives you 1/2. Or if I were to say 2 and I divided that by 4, 2 divided by 4 is still going to equal 1/2. So the decay in this case, 1/2 is actually less than 1. So this is a decay, exponential decay. But that is how I would get the function. Whether it's growth or decay, you'll still do the same thing. You always take a number in the chart and divide it by the number above. That gives you the growth or the decay factor. And as you can see, this is less than 1, so it's decay. And that's how we get the function. But there are going to be times when you don't have the initial amount right off the bat, and you have to actually find the initial amount. For example, here I don't have the initial amount. The initial amount is always when x equals 0. Well, there is no x equals 0, there's a x equals 1, but I'd have to go back one space to find that. But I'm still going to find the growth or decay factor the same way. I'll just take one of these numbers and I'll divide it by the number above. So if I took 144 and I divided it by 24, it's going to give me the growth factor of 6. Okay, so I get the growth factor, but if it's a growth question, just look at what's happening to these numbers. What are they doing to get from 24 to 144? Well, we divided and we got 6. So that means if I want to go down this chart, they're multiplying by 6 to get from one number to the next. Well, I need to back up and I need to go in a different direction. So I'm going to divide 24 by 6. So if you ever need to back up, just do the opposite of what you see. I see that 24 times 6 gave me 144. Times that by 6, that gave me 864. But if I want to go backwards, I have to divide 24 divided by 6, and that's going to give me 4. So the initial amount here would be 4. So it'd be 4 times 6 to the x. That would be my function. I just had to go backwards one space to figure out what that initial term was going to be. So always make sure when you're looking for the initial amount that it's when x equals 0, not x equals 1. It's not the first number on this chart. If this is a 0, then yes it is, but you have to make sure that that's your initial amount. We're also going to be graphing exponential functions, so you want to know how to match an equation to a graph, and the easy way to do that is by finding the initial amount. Okay, so in this function, let's just look at this first one up here. Y equals 3 times 2 to the x. Well, the functions we looked at earlier, this first number here, 3, is the initial amount. So what you'll notice is the initial amount, 3, matches up with the y-intercept. It crosses at where y equals 3. If I were to change the initial amount, let's say I changed it to 4, and I create this new line. I'm going to use the same rate here, y equals 4 times 2 to the x. All that did was it took this original function and it moved the y-intercept up here to 4. That's the initial amount. When x equals 0, that's my initial amount. But what we're going to be looking at is what we call transformations. So let's go back to our original function, y equals 3 times 2 to the x. If I want to move this initial amount somewhere, and that's how we're going to trace where this thing goes, is I'm going to start from the initial amount 3. If something happens up here with x, let's say that I took 1 away from this exponent right here. I've got 3 times 2 to the x power. If I take something away from that exponent, it's going to shift my initial amount to the right. So a negative will shift you to the right, and this moved me to the right 1 space. Now remember, my initial amount was here at y equals 3. All I've done is I've taken away from the exponent. That shifted me to the right 1 space. That's how I know what this graph is going to look like. My initial amount was here. It moved right 1. Okay. Now if I add something outside of that exponent, let's say I say plus 2. That's going to take my initial amount and it's going to also move it up 2. So I've done 2 things to this original graph. Okay. I've taken it to the right 1 and I've moved it up 2. So it did start here. That was my initial amount. I went right 1, up 2, and I still meet my graph right here. So that is exactly where I would expect that point to be. Right 1, up 2, I should hit this line somewhere at that specific point. Alright, here I've got these 2 functions, and you'll notice this first one, 3 times 2 to the x, is here in red. The initial amount was 3. So this first graph here in the red, it crosses the y-axis where y equals 3. So that's my initial amount, and that very same function has been transformed. You'll see here that it says plus 2. You got to the x power plus 2. That's going to move me to the left 2 spaces. So I'm going to be taking this initial amount and I'm going to be going to the left 2 spaces, but it says minus 3. So not only am I going left 2, I'm going down 3. So from the original starting point, I'm going left 1, 2, then I'm going down 1, 2, 3. And you'll notice that on this function, that's how I could figure out what transformation has taken place. If I was trying to match this equation to the graph, I would just start from the initial amount. I would start from 3 and I'd say, okay, from this point right here, what's happened? All right, now here's a good example of what this would look like on a test question. You're going to see 2 graphs and you got to figure out which graph matches the function. Always start with this initial amount right here. So in this case, we've got 2. That's our starting point. So I'm going to start at positive 2 on this graph, and I'm going to look at the changes that take place. You'll notice that over here it says plus 2. That means I'm actually moving to the left. Anytime they add to the exponent, you're moving to the left. So I'm going to go left 2 spaces, 1, 2, and then this one's telling me to also go down 2 spaces. So if I go down 2 spaces, that's no longer on this line. I'm not hitting this line at all. So if you look over at the other graph, if I start from the initial amount, positive 2, just like we did on the other one, this time I'm going to go left 2, 1, 2, and then I'm going to go down 2, 1, 2, and you'll notice I actually hit the graph. That's how I know that this one is the correct graph, because when I start from the initial amount and I move the 2 directions that it shows, it's moving me left, right, up, down, and I should hit the line somewhere.